Here, we learn the concept Maxwell right-hand thumb rule in the case of linear conductor from the chapter Magnetic Effects of Electric Current from class 10. So before getting into the concept, I just want to discuss what is Maxwell right-hand thumb rule. So it's a mnemonic to determine the direction of magnetic field around the current carrying conductor. You might already learn that if you observe a current carrying conductor, it produces the magnetic field around it, right? Through Oersted experiment, we learned that. Whereas to know the direction of this magnetic field produced around a carrying conductor, we use this thumb rule, a Maxwell right-hand thumb rule as a mnemonic. Okay, let's see how we can use this thumb rule to determine the direction of magnetic field around a current carrying conductor. First, assume that if you grasp a straight wire or if you hold a linear, straight wire means here linear conductor with your right hand so that your thumb points in the direction of conventional electric current. So you know the direction of conventional electric current. That is, if a battery is connected to a wire, the current direction will be from positive terminal to negative terminal. This is the conventional direction of electric current, right? So in the same direction, we should take a thumb pointing in the same direction. Then the direction of fingers curl around. So the four fingers, the remaining, except thumb, the remaining four fingers, they are curl, right, around the wire. These curl fingers shows the direction of magnetic field lines around that wire. Okay, we will see it how in detail. So this statement will give us the Maxwell right-hand thumb rule. If you grasp a straight wire with your right hand, and if you stretch the thumb showing the direction of electric current through that conductor, then remaining curl fingers around that conductor will indicate the magnetic field direction. Okay, that is Maxwell right-hand thumb rule. And this is also said to be the right-hand grip rule, or we can also call this as Maxwell corkscrew rule. Okay, yes. We use this rule not only in the case of linear conductors, but also we will use this in the circular loops also. Okay, further we will see that how this is used in the circular loops. Moving to the next one. So here you can see a figure. Okay, let's say this is the conductor. You can see here this is a conductor. Okay, the straight rod is a linear conductor. You should hold as shown in the figure with your right hand, showing the thumb, pointing the thumb, or stretching the thumb in the direction of electric current. Let's say the direction of current is shown with this arrow mark here, right? The current is moving in the upward direction. So these curl fingers are showing the direction of magnetic field, right? You can see that the current is moving up and the curl fingers are shown in the anti-clockwise direction, right? Yes. So when you hold this conductor with your right hand, showing the current direction, okay, with your thumb, then the curl fingers will show you the direction of magnetic field lines produced around it. Okay. Yes. And next, we can see two cases here. Let's say here we see it in the upward direction and in the downward direction. Let's assume that as we have seen in the previous case, the current is moving up so that you can see that the curl fingers are in the anti-clockwise direction, right? Yes, this shows the direction of magnetic field. Here, when the current is in upward direction, your thumb is pointing up and your curl fingers are in the counterclockwise, nothing but anti-clockwise. Okay, which gives us the direction of magnetic field. Whereas if you take the current moving in downward direction, here you can see that the current is moving in downward direction. In such a case, here you can see that the curl fingers are in the clockwise direction. Here you can see that this magnetic field produced around the wire where the current is moving down is in clockwise direction. So if the current is moving downward, the thumb is pointing down, right? When you hold that linear conductor with right hand, stretching your thumb. And remaining four fingers that are curled around the conductor are in the clockwise direction, which shows the direction of magnetic field, right? So here we can say that if the current is coming out of the page, assume that the current is coming out of the page, then the direction of magnetic field will be anti-clockwise. So here you can see that this represents the direction of current, that is the current is coming out of the page. In this case, the direction of magnetic field around that linear conductor is anti-clockwise. But in the second case, let's say the current is moving into the page. Then in this case, the direction of magnetic field produced around that linear conductor is in clockwise direction. Clear? Yes. Here we see the patterns of magnetic field lines around the current carrying conductor. Okay. So here you can say that, yes, you can see that the electrons, they given the electrons direction here. The electrons are moving from negative terminal to positive terminal. So what is the conventional direction of electric current? The conventional direction of electric current is from positive to negative. So that you can say that the current direction is upward here. So just now we have seen that if the current is moving in the upward direction, what is the direction of magnetic field? The direction of magnetic field is anti-clockwise, right? You can find anti-clockwise direction of this magnetic field here. But here it is reverse case. The current is moving down, so that the direction of this magnetic field is in clockwise, right? Yes. Now we see these patterns around. If you say the iron fillings are taken and they are spread on the cardboard around the linear conductor in these two setups. If you turn on the key, when the current is passing through that conductor, it produces the magnetic field around it. And when you gently tap that cardboard, you can see that these magnetic lines makes these iron fillings align themselves in the particular pattern. So here you can see that they arrange themselves in the concentric circles, right? Around the linear conductor. What is the pattern of magnetic field lines that you see? Concentric circles, right? You know that concentric circles are the circles which are having a common center and they won't intersect, right? Yes, this is the common center of these concentric circles where this center lies on the wire, right? And next, if you observe the distance between one line to the another line, here you see that the distance from one line to the another line, as we are moving away from the wire, it is increasing. That is, if you move away from the wire, the magnetic field strength decreases, right? Yes. Here you can see if you move closer to the wire, the magnetic strength will get increases. That means, let's say, if you observe the magnetic strength at this point, the magnetic strength will be more. Let's say this is point X and this is point Y. somewhere in the magnetic field, we have taken 2 points. Let's say this is X and this is Y. Here you can see that at point X, the magnetic field strength is maximum. Why? Because it is closer to the wire. Whereas the magnetic field strength is minimum at Y comparatively with X. Why? Because it is far away from the wire. Okay. Yes. So finally, we can say that these are the three factors that influence the magnetic field lines. So one is direction of current. If you reverse the direction of current, magnetic field direction also get reversed, so that the current direction will determine the direction of magnetic field, right? Next, current strength. Let's say if you allow 1 ampere of current is passing through the linear conductor, it produces some magnetic field. And if you increase this strength of current to 2 amperes, then the magnetic field strength around that conductor also become strong. It produces the strong magnetic field with the strong current. Okay. And next factor that influence the magnetic field strength is distance from the conductor. As we discussed just now, if you move away from the wire, the field strength decreases. If you are closer to the that is current carrying conductor, magnetic field strength will be more. So that the magnetic field strength decreases as we move further away from the conductor. Then, so from this we can say that magnetic field strength is directly proportional to the amount of current passing through that conductor. And here you can say that magnetic field strength is inversely proportional to the distance from the wire. Distance from the wire. Done.